Unit 1, Lesson 5, so we're doing composition of functions. I'm going to go over these word problems because these are applied. They're kind of nice to see why we want to do compositions. And then the last class is the investigation part, that part that kind of draws it out. We're going to just not do very much of it, okay? Just because it just took a little bit longer. They didn't think it helped them, and then once we started just doing the actual work, they're like, this is so much easier. So you guys get the benefit of not having to see that. If you do want to see it, just let me know. There's really not much work. It's what they're doing is, I'll just give you the summary now, is that they are saying, here's a function that was a composition. How could it be like two functions together? So how could you unwrap the composited? Let me see, what the composited function to the previous two, like how it started. And so you kind of go backwards, like the unwrapping method. So anyway, this part's good though. When a pebble is dropped in a pool of water, ripples in the shape of circles form on the surface of the water. So we know that you drop something, it's a bunch of rings, okay, and it has an equation for how those ripples grow. 0.3t, okay, where r is the radius. So that ripple as it comes out, it's growing at 0.3t. So every second, the ripple's growing by 0.3 of t. It says if the area of the circle is a equals pi r squared, combine these two formulas to figure out the radius formula in the terms of how it's growing the area in terms of time. So how the radius is growing in terms of time, we would sub in to r for the area. So we know the radius is growing here, okay? That's the radius how it's growing. And we want to know how the area is growing with respect to time. We would go ahead and put it right there. And now we have a function of time. Okay? So then if I want to see how the area is at 6 seconds, I can now plug 6 in. If I plug 6 in here, that's not what we want because that's the radius, right? So you would simply just go a equals pi times 0.3t squared. You would sub it in. Okay, and again, this represents the ripple to write a formula for the area of the circle ripple after t seconds. So the area in terms of time. Okay? Any questions on that? Okay. So now let's look at B here. So when we have B, this part's just kind of irrelevant. It's a bunch of numbers which I don't like. Makes you like, what is that? 3.5 liters V6 2012 Toyota Camry. Okay, just so you know the specifics. Has 8.2 liters per 100 kilometers. The cost of gasoline is $1.25 per liter. So the first thing you're going to do is the volume of fuel used can be written in the function of distance traveled. So complete the following for L in terms of D. What they want to do is liters, your liters function, they want to know in terms of distance. Like how much distance does the liters go? Now when we do distance, we'd like to use singular, okay? We like to use singular numbers. So right now, what's our comparison? Our comparison is 8.2 liters per 100, right? So we'd like to get that so it's not per 100, but per 1. So how can we do that? So we know it's 8.2 liters per 100 kilometers. And if we want to get that in terms of 1 kilometer, divide by 100, right? So we just divide by the 100, so we know that D, okay, it's going to be 0.0. Do I have a 1 on there? I don't know why I have a 1 on there. Just point. It's just 8. Oh, that's an L. Okay. Dang. Okay. It's fine. Just restart. So you can't read your own writing. That's a weakness. All right. Sorry. So then, yeah, divide by the 100, so you get the 0.82. Okay, that's where it comes from. So, yeah. Let's try this one more time. Sorry. I just want to have it right on here. So it's 8.2 liters. Then we divide by the 100, divide by the 100, and that's what's going to give us 0.08, because we moved the decimal over twice, 0.082 D. Okay, so that's the distance per liter. So like, for example, if I put in 1 here, that's how much liters of gas it would take. Okay, which is not very much, right? If I put 1 kilometer, it takes 0.082 liters. cost of the gasoline used can be written in the function of L. Complete the following. So we know the cost is simply just what? Just 1.25 L. Okay? Well, cursive L so we can see the difference between the ones. Okay? Now here's the composition part. We can find the cost of gasoline in terms of distance traveled by combining these two functions. If we substitute the formula for the first function into the second, because this function is a function of L. That represents the liters, right? So if we take this function, we put it right here, we now have the cost function for how far we drive. So it'd be 1.25 times 0.082 D. And I'm going to simplify that further, and then I'll step away. So your cost function is 0.1025 D. Can somebody tell me what that means? Like just in terms of words. What does 0.1025 mean? Yes, but in terms, this is the cost equation, right? And we just got this in the form of a function of D. So we're pretty much what we're doing is we're figuring out the cost per distance, right? So what this is saying is it's 10 cents per kilometer. It's 10.25 cents per kilometer is how much you pay to drive. So that's what we've come down to from the top. You figure out it costs about 10 cents per kilometer to drive. Okay? That's what we've broken it down to. Okay? Okay. So, like I said, we'll kind of skim through this investigation here. I want to see composition. So this is where they're unwrapping, like I was saying. So this is what you want to go for sure. You got to know this part. So the composite function is when you are thinking g of f of x, or you can write it g open circle f. And it's always the second one, and what's inside is what you plug in. Okay? I'll show you with the one at the top here. So if I want to do g of f of x, that means I'm going to take f of x, I'm going to put it in for the x in g. Just like when we say, just if we did g of 3, right? That means we put 3 in for x, yeah? Same thing here, but it's a whole function, so that's kind of weird, but same process. So 2x just goes there. That's what it would be. The 2x just went where the x was. Now, some people keep asking, well, what happens to the x? Well, you're replacing the x. Okay, so I'm right here. F of x went into g of x for x. So this function replaces the x here. That's all we did. That's how we do composition, or composite function. Okay. Let's do it the other way. Let's do f of g of x. Same, there's one at the top there. So I take this x plus 3, and I put it in there for x. So it's going to be 2 times x plus 3. And if I simplify that, it would be 2x plus 6. Okay, so there's your f of g and g of f, just for that simple example there. Okay, questions? What do you think, Hannah? Cool. Yeah. Thanks. All right. Okay, so like I said, we're going to skim this part. This is still the unwrapping part. Okay, so we'll get to the kind of the basics here. So right here's what you want to go with next, I'd say. This is the steps that we're going to use to do composition. So I actually would say that a lot of books don't have great flow charts or great steps processes, but I think overall these types of books, the 20, 30, and 10 books, when they do their little flow charts like this, I think they're pretty good. Okay, so this says, first thing you're going to do is you're going to start with your composition. Which one are you doing? Are you doing gf of x or f of g of x? Which one? Replace the f of x with the formula for f. What they're saying is formula is the function. So if you want to change this to function, you can. I didn't really like the formula word. Okay. And then apply the formula or function for g. And then write the answer in simplest form. So we're going to do these steps right here together for example 3. Okay. So start with g of f of x. That's what they did first step for us. 2, replace f of x with the formula for f. So f is 10x plus 1. So we're going to write it as g of 10x plus 1. And now we sub the 10x plus 1 in the x for g. 2 times 10x plus 1 minus 5. And now we just simplify. Okay. 2 times 10, 20x. 2 times 1 is 2. So it's going to be 20x. And then 2 minus 5 is minus 3. So we're 20x minus 3. And that's it. That is your g of f. Okay, questions? Okay, we can slow down a little bit because I'm not speeding through the stuff I said that we were going to kind of skip. So feel free to ask questions now. We're going to go down to example 4 next. And then we're talking about the domain and range a little bit. Okay. So example 4, we're doing g of f and g of g. So that means you're plugging it back into itself, which you also can do. So g of f, we're going to rewrite it. So that's going to be g of 2x squared minus 1. So I entered the f of x there. Now I want to plug that in. 3 times 2x squared minus 1 minus 4. So there's the g of f. Three times 2, 6. 3 times negative 1 is negative 3 minus 4, negative 7. So your g of f of x is 6x squared minus 7. Okay, go ahead and try g of g on your own. Pause the video. I'll let you guys try it. I'll walk around, see if you have any questions. G of g, how do we do? G of g? Anybody have it? Okay, so let's see. So we're putting g back into g, so we are going to put a 3 here, and then we're going to insert the 3x minus 4 here again, and then the minus 4 there. So yeah, I think you went as far as you could, Hannah. So 3 times 3 is your 9x. 3 times negative 4 is negative 12 with the minus 4. That's as far as you can go. Yep, that's g of g. Okay. All right, so let's talk about the domain. This is pretty much our last page. Okay. Domain and range of a composite function, okay? So consider functions x squared minus 3 and root x minus 1. So we're considering those two functions. So we're going to go ahead, it says without finding a formula for f and g, f of g and g of f, go ahead and evaluate. So what I did on these ones is I went ahead and just said, well, what is f of, this is what they mean, f g of 2. So what's g of 2? 2 minus 1 is, right, right here, 2 minus 1, 1, square root 1, 1. So we're just plugging a 1 in here. 1 squared is 1, minus 3, negative 2. So this one ends up being negative 2. And so what they mean by is without finding the formula, so without making the composition. We're going to do the composition still in a second. That comes down a little bit later here. So if you didn't follow me, because we did a little bit of mental math there, is I took 2, I put it in here for g. Okay, that gave me 1. And I took right here, this is now, this whole group is a 1. So I did f of 1. 1 squared minus 3. Now, f of g of 0, what happens when we do that? So if I put 0 in for g, what happens? You should immediately be like, yeah, you get a negative in the radical. If I put a 0 here, 0 minus 1, can't square root negative. So this is a D and E. We can't do it. That does not exist. It's not in the domain. Okay, let's look at g of f. So now we're doing it backwards. We're going to look at 2 in f. So 2 in f is 4. 4 minus 3 is 1. So that means we're doing g of 1. Put 1 in there. 1 minus 1 is 0. So 0 is part 3. Okay. So I'll show you the steps here a little bit slower. So if I do g f of 0, so I put 0 in to the first one, I get what? If I put 0 into f, what do I get? Minus 3. Now, if I put, now I want to find g of negative 3. If I put negative 3 in for g, what happens? Negative 3 minus 1. Negative 4. D and E. You can't do that. That's a problem. Okay, good. Okay, so what is the domains of f by itself? That's a parabola, so what's the domain of a parabola? All reals. So XER. What's the domain of g? It is a radical. It's a radical function. So if you think about it, if I put 0 in there, is that good? What makes the inside of there 0? 1, right? And we can have 1 and bigger. So you're going to say x is greater than or equal to 1. And this is your set builder notation. Okay? So x is greater than or equal to 1 for the radical function. Now let's talk about the ranges. Well, what type of function is x squared minus 3? Quadratic. Good. I'm hearing you guys say these things now. That's important. It's quadratic. Does quadratic have range restrictions? It does, because remember, it's got a min or a max, because it bounces. Okay? So this one's a very simple one. It's x squared minus 3. So it's just simply negative 3 is the minimum. So the range is greater than negative 3. Okay? All right. Range for f. Y. Okay, good. And then g. What is the range for the radical function? So if you forgot, remember, a radical function is going to look like this. That's what it looks like. What's the range for that guy? G. G's range. Not 1. That's the x. This greater than 0, right? And that makes sense, right? Nothing that outputs from a radical is going to be negative. Nothing that outputs, the y's, is going to be negative. Okay? All right, so what we're going to do now is we're going to look at these 2 pictures that they said Aaron, I think that's the name, yeah, drew to represent the functions of f of g and g of f, and we're going to figure out where he went wrong. Okay? So, first thing I want to do is, he obtained the following graphs. He concluded this stuff. There are errors in his thinking. So what we're going to do is we're going to find the expressions, okay, of what f of g is and g of f is. So I'll move this up so the graphs stay there. Okay, so f of g. So f of g from the top, we're using the same functions. So we know that we're putting g into f here. So that means it's going to be, so here's f, just so we have for on the board so we can see it. And then we have g there. So that means we're taking this and putting it right there. Okay, so it's going to be for f of g, it will be x minus 1 minus 3. Now, they cancel here, so you get x minus 1 minus 3, so you get x minus 4. So x minus 4 is a function of f of g, but we're going to come back to that. See this here? That's actually what that is. That starts at negative 4, up 1 over 1. So his graph is mostly right. We're going to talk about, here's a domain issue. Okay. Okay, let's do g of f over here so we see what that looks like. So g of f, so that means it's going to be x squared minus 3 is plugged into the x, minus 1, which makes it x squared minus 4. No, you can't square root those. They're connected. It's got to stay like that. So that right there is your g of f. Okay? So let me explain this picture for you. X squared is still going to be eliminating negatives. So whenever you see an x squared in a graph, you got to think, well, it's probably going to be mirrored. That's why it's mirrored here. Okay? So what's happening is that if I put a 0 in, what do we get? See how there's nothing at 0? Because that's not allowed. If I put a 2 in, what do we get? 0. So that's where actually he's wrong. See that? This should be down. Okay? If I put a 1 in, let's just keep hammering this home. 1 squared is 1 minus 4 is negative 3. That's why there's no values here. Because I got a negative. Okay? Let's do 5. Or sorry, let's do something easier. Yeah, no, 5 squared is fine. No, 3 squared. 3 squared. 9. 9 minus 4, root 5. Root 5 is slightly above 2. So you see this right here? Slightly above like 2. So he just didn't bring that all the way down as his only error. Okay, but the mirror happens because if I put a negative 3 or a positive 3, I get the same answers. See, they're just going to keep growing the same in opposite directions. Okay, so we got the expressions. Use the expressions indeed to figure out the following, so figure out what happened with his graph. So can we figure out what's wrong with the x plus 4? It's a little bit tricky. We kind of skimmed over it a little bit. What was our domain at the top? What was our domain at the top for f and g separately? Yeah, x is, say that again? Oh, yes, at the very top. Sorry, the part B on that page. The very top there, after we did the first set of 4. So you had x, oh, sorry, you have x equals r, yeah, there. Okay, sorry, I see what you're saying now. X equals r there. Okay. But what changes for this one? Let me reword it. What changes for this one? So I want you to look at this part. This is where it gets a little bit tricky. So we put g into f, and so we put a square root, and we have it squared, right? And so when we look at that, and what's the second part? Sorry, it's the minus 3. Sorry. Okay. So what I was asking, so Maddie said it right. Sorry. Maddie said it right. It is still, we said at the top, it's xer. Sorry, I'm losing my thought here for a second. Xer was for your function of f. But our function of g was what? Our function of g was x greater than or equal to 1. Right? And that's because of the radical. what you need to know is that still holds true in the composition. So we can't just say, oh, cool, those are gone. Our domain is better. We still have to remember the function's domain independently and the composition. So what happens is that they above did not consider this that we had at the top. And so his graph needs to be cut off at 1. So the x minus 4 here, it goes up 1 over 1. It should start there. And that's where it should go. So there shouldn't be anything down here. 1 and to the right. Yes? What goes, yeah. Okay, so what she's saying is see how this one right here? That one's all reals, no restrictions. This one had restrictions, so this is the one that we're going to make sure to keep an eye on. Okay, and so that's what we're talking about. Okay, this one they just graphed wrong. Okay, so they actually weren't too bad on the restrictions. So this one was at 2, it's going to be 0, so this one goes more like this and like this. Might be a little bit steeper than that, but it should be better mirrored, just obviously not perfect. So domain of this one, of f of g, is x greater than 1. The range is going to be what then? So what's this point here? Where's it at? It's at negative 3, right? So it's going to be like that. Domain of the second one. So, sorry, why is this negative 3? Because we've moved over. It goes through negative 4, but at 1, it starts at negative 3. So this point was 1, negative 3. So that's where the range has to start, too. Okay, and this one. So domain of this one's a little tricky. How do we write this one? Greater than 2, but less than negative 2, right? We want numbers outside of the 2's. So you'd say x less than negative 2, x greater than 2. And what's the range for that one? You guys should be able to get that one just from looking at it. Greater than 0. Okay, very good. Okay, just the very end here is just going to summarize what we just kind of did, and then you guys will be good. I'll actually put the dash back up. I still want you to write the dash down. Okay. All right. So when we calculate the expression for a composite function, there may be restrictions on the domain and range. In most cases, the domain and range of the composite function will be different from the domain and range of the original functions. So they still can change, okay, but like Steph said, which is helpful, the most restrictive usually carries through. Okay, the most restrictive is one that you're going to account for. Okay, but you do have to, obviously, that last one we did, though, was neither of them, right? So you got to keep that in mind, that between 2, 1, that one we got from the picture itself. Okay, the domain of the composite function f of g cannot be more than the domain of g. The range of the composite function of f of g cannot be more than the range of f. So you can't gain domain values or gain range values with a composition. So what it's saying is that, as again, what Steph said, if f has a restriction of 3 and higher, I can't now say all reals for my composition. Has to be at least the 3 or higher at a minimum. So once you do the composition, you won't gain domain values, if that makes sense. All right, let's stop it there.